All right. So I have 40 slides. I try to finish in 40, 45 minutes, depends on my speaking speed. There's significant amount of overlap. Uh, the talk I gave about the peripheral measures in fMRI last Thursday, I tried to make it try different. I will explain more physiology and emphasize how we measure signals and how do we measure signals as a source. Um, Changes the way we understand the signal, and if you want to remove it or if you're interested just the signal. And yeah, so it will be a big overview, and through the end of the talk I will give some examples of methodology that I'm trying to build, and also a lot of literature citations. Yeah, I like to the pictures from Eindhoven. I will come into that. I like to give historical uh, pointing and studies. But yeah, as an engineer, I would like to uh, give an overview in a spectrum. I mean, when we talk about physiology, there are biological rhythms that are oscillatory from orders and orders of magnitude, from changing in milliseconds to over years, basically. Um, so, I mean, we have neuronal oscillations that is in the range of hertz, can go to up to hundreds hertz. And there's like gamma, beta. They're well known in the EEG literature, which will be another course next week based on EEG, the neuronal firing rates and everything. Uh, there are like relatively slow things happening, like heartbeat, for example, every second it's beating, and slowly going to even slower breathing. For example, we breathe every 3 to 6 seconds. And there's a phenomena called Maillard waves, which is more like a blood pressure oscillations happening in our veins, which is very species specific. But most of the mammals it's zero point 0.1. Some rodents it's more higher. There are like if even further slow things happening called sympathetic and parasympathetic balance that is related to our stress level and uh, alertness, drowsiness that is happening 20 to 40 seconds. And there's a lot of vasculatory things that are overlapping with this um, um, biological rhythms. And one, I mean, autoregulation and vascular tone is one of it. I mean, there are like hormonal changes in the body that changes vasodilation and constriction, that changes the signals we are measuring, that changes the perception or all the body state and also the neuronal state. There's, needless to mention, sleep rhythms that has its own literature and own study that will cause you get in the scanner, sleep overnight, because that has a lot of different spectrum of signals that you need to measure very long. Um, I don't want to go into detail about circadian rhythms that can be a day, so very ultra slow things. I mean, talking about neuroplasticity, learning, and other things like, for example, menstrual cycle, which is month, which is like microhertz. That's very, very slow. So everything the thing we want to measure, or we want to see the blood the blood oscillations or vascular things, and it completely depends on how we measure things. So if you think you go in a scanner that you stay 10 minutes to an hour, so there are a fraction of things we can measure. And other slow things will be just a tangential ramp maybe in the signal, or the fast things happening we don't see at all. Um, I haven't seen, I was looking at the literature if there's a relation between the size of the system and the speed of the biological oscillations. To me, there should be. I mean, it makes more sense if you make the assumptions of if you go to molecules, things are happening more fast. If you go on the more larger scale, like brain or like vascular things, because a lot of volume needs to move, things start to happen slow. That might be a not wrong assumption. So as we talked about measurement speed and oscillations and biological rhythms, I think we can move forward, and we can look at like signal characteristic. What are the characteristics of physiological signals? I think that's so we, for example, inhale and exhale. It looks like regular sinusoid up and down, which brings us, or like you see it in the second place, like is a electrocardiogram, which is heartbeat, electrical activity of the heart. They're repetitive, like they're periodic. But on the other hand, that there is a huge amount of variability and interaction to each other too. That actually make the periodicity maybe quasi-periodic, because the periodicity, amplitude, and the phase can change in the time, and they can interact with each other. So that makes the understanding is a little bit complicated. Needs like information about the physiology, the measurement, and the timing. Next. Yeah, here we see the Willem Einthoven. That's kind of a standard to measure the cardiac activity, which is the main driving force of the all vascular blood movement, blood pressure in the body. And here we see his galvanometer. He basically dipped his hand and the leg in the saline water, trying to measure the electrical activity in the old time. I mean, we have a little bit more advanced approach right now. I mean, this is basically a kind of a dipole source in a system that you kind of to triangleize and then understand how the heart contractions happen that creates basically the electrocardiogram. I mean, in the clinic, if you go in the clinic, you have multiple electrodes attached to your torso to have all the detail you need to have about the cardiac activity. With the MR scans, we measure it slightly differently because we don't have that. If you want, we can have that, but there are other technical challenges I'll come into. We have a device that comes with the Siemens like this. It both measures your respiration and the cardiac heartbeat. It has 3 electrodes. It has a lot of attachments on it to reduce the amount of artifact, because MR is magnetically very noisy environment. What you measure has a lot of noise induced on it. And we have in MR devices this what called biopack. This is an amplifier. This amplifies the signals you measure with the attachments you put on it. Things are easier outside of the MR if you want to get information about the physiology, but if you want to do it with the scanner, particularly in MRI, there are a lot of challenges come into. For example, the electrical activity of the heart. At the top row shows it's outside of the scanner measurement, but the down, that's what you get, because there is a magneto-hydrodynamic effect. Basically, your body is magnetized and your blood is moving around, and then it changes the signal you try to measure electrically. And in some cases, it is not recoverable. Some cases it is, but you want to basically detect the peak at least to know where the heart rate happened. It's called QRS peak. I mean, in this case, for example, depends on the artifact and your body position, it may not be recoverable easily. That's another reason why we measure the heart rate from the finger, because it's optical measure. It has less sense. It is not sensitive to magnetic electric changes. It's different way of measuring signals. But then the question is, how accurate is the pulse rate variability you measure from the finger estimates the heart rate variability, for example. I mean, after the heartbeats, the blood arrival time to the finger is different, the shape is different, and there's also a vascular changes in the periphery, which may further expand the signal back and forth. But most of the studies are using finger signal, which is delayed and might be expanded to as a proxy for the heart rate monitoring. I mentioned this last week. I mean, finger is kind of easy to attach, but you can measure this optical measure to other body parts. That has some advantages that is not studied with the fMRI, especially the tweak the signal properties of the pulse, which is the second peak, is very informative on the blood pressure and the secondary physiology thing. And it's kind of dampened out if you try to measure from the finger or the ankle. It's just the one tip of a signal. But if you measure from the neck, for example, you start to get the secondary peak, which is kind of a reflection, and that gives you more information about the heart output, stroke volume, and blood pressure, which is more available with ECG, but less available with pulse oximeter. And I put the link of this chapter if you want to go into detail of this. So basically, getting all the pulse features of the systolic and diastolic. More we have this blood pressure. I mean, this is pneumatic, so this is different than the optical. It has little touch more sensitivity on the secondary peak because of the optical properties of the second peak are different. But moreover, we can do this pressure measurement right at the neck, which can be more sensitive in this small pulsations in your neck. I mean, there's a carotid artery passing, and it is right in between heart and the brain. So one good thing is the signal you measure right here is happening less delay after the cardiac output. So you can relate more directly with what's happening in the brain. Second, you get the more characteristic peaks, a little bit more rich. And of course, it comes with the caveat, like if you move your head, since it's pressure sensitive, then you get a lot of nuisance signal on it too. So it may need more conditioning. But that might be kind of an additional measure to get more information if the ECG is not available. Talking about respiration, it's probably the most physiology. The signal drives the physiology we see in the time series. It's typically measured with this kind of a bellow wrapped around the belly, just measuring your chest size. So you inhale, it just expands, and then it converts the expansion into electric signal, and then we get signals like this, so up and down. So if subjects happen to inhale more, so you see more higher peak. But that's not the only respiration in the field. There's also thermistors, which you put in the nostrils, and there's this study kind of compared all of these. I mean, it's very uncommon not to measure the bellow. But there are subtle but very important changes because respiration is very subject specific. Some people do very shallow breathing, so their chest is not moving much. But if you put this thermistor in the nose, then you started to see the temperature changes because you exhale like high temperature, more warm air, and then you inhale, then it's colder. So it's kind of, it creates similar pattern, but there are like delays on that pattern. So one can kind of do shallow breathing, and the other subject could be more diaphragmatic, so that causes the chest move. So there are like, depending on the sensor you use, the signal you measure is completely or like slightly different. Coming to the actual measurement, actually, like what is functional MRI and what's typically used? It's basically T2 star weighted images. If you listen to the earlier talks, the T2 star is sensitive to the deoxyhemoglobin in the blood. And this is called BOLD, the abbreviation, blood oxygenation level dependent. This is a nice kind of an overview what happens during the activity, and there's like multiple changes going on. So for example, if you focus on here after the task started, so the cells around, they started to consume the oxygen, which causes the deoxyhemoglobin to fall down, which creates the carbon dioxide concentration high, and then it triggers a vasodilation, and the flow comes in to wash everything out, which causes the oxy to further fall down. Um, this is called basically a hemodynamic response function, and this is a indirect measurement. So what we see here is kind of a filtered version of what is happening actually in the brain. And as you can appreciate, it's more dependent on flow. And this is highly nonlinear, as in earlier talks it's mentioned, like even the small task can cause this kind of thing. And it may be saturated if you increase the amplitude of the task. So if you look at closer, neuronal activity is far behind, that the MRI signal is, there's a lot of steps in between which causes the signal we measure. And actually, if you look at the signal, the oxyhemoglobin is very related with the respiration as we inhale and exhale oxygen and carbon dioxide, and the blood flow is very related to cardiac pulsations, which will be the core of this talk. And if you look at, I mean, they're like direct relations, they're indirect relations. I like this slide because it kind of shows it is very entangled to each other, because the, there's like vascular pulsations, obviously directly from heart to brain, but there's also brain controls the heart, which is a cardiac control. There's respiration, and there's also interesting effect that when you inhale, the thoracic pressure is different, then the heart tends to beat more. So there's like respiration and heart rate. And there's CO2 modulation, which is a vasodilator, which also is respiratory related. And there's, most importantly, perturbation of magnetic field. If you're in the magnetic field and you inhale, it changes the main magnetic field, which causes an MR signal to go up and down, which I kind of summarize here. Yeah, we can say the hardware-related things as a noise, like, if there's a ramp or if there's a magnetic field perturbation. Although they cause with physiology, they can be named as a noise because we know it happened due to the measurement error. Things like hardware-related things like scanner drift and thermal noise. And motion is very interesting thing, in my opinion, because everything can be translated into motion. And later in the talk, I will talk about more nonlinear motion. The head motion actually can be caused by the cardiac pulsations. I mean, when you kind of put your head in your hands, and then you feel the pulsations on your face, in your eyes, in your neck, it's kind of makes sense that all the ballistocardiographic things, like pushing the brain to the up, but head motion can be unrelated from physiology to like voluntarily things. Yeah, and also nonlinear things like blood flow can cause a vein to expand. But there are more into this, like there are more liquids in the body that are indirectly modulated by the physiology, like CSF. I mean, CSF, its own thing, kind of, and it has some coupling with the blood flow because of the Monroe-Kelly doctrine, which says basically the skull has a limited area. So if there's a blood rushing through the arteries in the brain, something should go out, which will be the CSF. But the thing is not happening linearly and direct, because the circulatory motion of the CSF is kind of, maybe it's delayed, and maybe it is not well time locked. And this is studied more like in the glymphatic literature. But the more into it is the arterial blood pressure, which is kind of a secondary relation to the cardiac output. That has also some receptors in the brain that senses, hey, the brain has high pressure now we need to lower the heart rate, which is basically sympathetic and parasympathetic balance of the system. Now we come to the time series analysis, basically the functional MRI. I mean, the previous courses has mentioned this a bit, but I will try to recap in one slide. Um, they're not ready to do statistics, or they are not ready to measure the physio right away from the scanner. I mean, when you get in the scanner, you get a bunch of images like this. So they need to be aligned in a space and time. And then we look at the time series. And it usually looks like this. And it's kind of frustrating why it looks like this. So there's kind of drift that comes in, which might be a source of information, but it's typical analysis is we just align it back to normal because of it's called in the literature baseline correction or trend removal. It could be scanner drift removal to condition the the um, um, the time series, the distribution of the temporal characteristics. And there are abrupt motions in the fMRI time series, which could be part of physiology, but it's usually regarded as a head motion, um, abrupt head motion. It could be a pulsatile motion if it's repetitive and periodic, as we mentioned at the beginning of the talk. And we like to correct those. For example, apnea has a function to do that at 3D spike, which is very handy. So this is basically done with the image alignment or registration or motion correction in the literature. So there are several terminology. To be sure, like external measures like, MOIR, um, head tracker, it's basically motion tracker, can be used externally to confirm that it's really the head motion. And there are tons of other filtering, spectral filtering, smoothing, skull stripping can be done in functional MRI. And as we all know, there are tons of software to handle these things. They have all positives and negatives. But coming to the physiology, I think improving temporal resolution is important to avoid the aliasing. So, for example, here I compared two imaging methodologies. On the left side is basically a standard one that is commonly used in neuroimaging studies called echoplanar imaging, which is scanning the K-space line by line, and it creates kind of fast, but not fast enough to sample the cardiac, maybe every 2 or 3 seconds. And on the other side, we just make this process very fast, just give up some image quality, but now we have better temporal resolution. Um, this this can go further to the very fast, like 20 images per second, probably not necessary to sample the cardiac, which happens usually every second. But the proof of principle, we want to see the effects as the measurement we are doing is very physiology dependent. So ideally, if we can scan fast enough, the respiratory signals and the cardiac signals we measure with those sensors should kind of align in time with the signals we measure. So this kind of a direct impact, direct influence on it. And we can look at the spectrum of it, which will fall into the spectrum I showed at the beginning of the talk, which is kind of 0.3 hertz, which is respiration, and about 1 hertz. It's very subject specific to cardiac pulsations. Yeah, following the temporal resolution, I mean, if you go further fast, you can start to delineate these pulsations, and not only temporally but also spatially, because there is a thing called like cardiac binning, respiratory binning. So you can take the snapshot images and put in alignment, and then see how these patterns propagate in the space too. So there is a kind of an image of it with this fast imaging technique. So if you just, when the imaging happens, and then if you just sort them in the cardiac phase and you get the average, this is what you get in the space. Kind of makes sense physiologically. The pulsations are kind of evolving from inner brain and then spreads out. And then respiratory is a lot more slower. But pay attention that this has very poor spatial resolution, so it doesn't tell much how it spreads in the vascular branch in the brain. It's more like a directional measure that the spatial temporal measure starts from the inner brain and then slowly spreads in the other part. More interestingly, there are like very, very low fluctuations that is happening 10 to 100 seconds. Uh, I think we don't want to watch it probably a minute. So it is not sure if it's meaningful neuronally. It's kind of also spreading around the. Yeah. So everything that, I mean, if we want to understand how this affect the signal we measure and what is the relation between it, the sampling rate is really important. In this graph, it shows how the sampling rate and where you can sample all the stuff. For example, you need to be at least 500 milliseconds of snapshots to get the cardiac sampling, which will be the twice as the sampling rate. Even faster will be better. But typical routine in the functional MRI, 2 to 3 seconds are common. So what it causes is all the signal physiology happening here is kind of aliasing back into the low frequency. So actually, we don't know what signal uh, we measure is coming from physiology or like higher frequency that is aliased into the low frequency. Um, Yeah, and then we can, if we have the enough sampling, we can differentiate the things happening unfiltered. We can filter them out, and then differentiate all of them. Talking about a little bit, um, for example, independent component analysis, um, it is heavily used technique, and that is not model driven. It uses one thing, which is nonlinearity, the non-Gaussianity of the signal. Because if a signal is oscillatory, it goes up and down, the temporal properties are kind of more like widespread. But if a signal is oscillating around the zero, more like Gaussian kind of thing, this is kind of the separation, how it happens. So it just separates the signal based of non-Gaussianity, but it is very manual thing. So you need to go into all components to look if it is meaningful or not, because it spits out a lot of components that you need to look at it if the space and the time make sense. I made a small simulation here. For example, imagine like three pulse style areas, like circles, for example. One presents a low frequency, 0.05 hertz, which is neuronal or vascular, you can say. One is like more respiratory, one is more like pulse style, like heart rate. And if you just subsample it and try to run three components of independent components, it becomes really hard to separate it. Because like if you subsample high frequency, it's basically a low frequency thing. But if you have a very high sampling, you started to have this overlapping components better delineated in the space. It brings the importance of the sampling, but not this time series sampling is the only thing we have. We can also understand how does it look like in the brain. I mean, these signals have very focal in the brain, which is following the brain anatomy. I mean, the respiration causes the sagittal sinus, which is the draining vein at the back, very sensitive to the blood flow, and the cardiac pulsations, which is around the arteries around the neck and also inside the ventricles. Talking about ICA more, like you can look at this components, even if you have the low frequency measurement technique, it looks very jagged and noisy, but when you look at the location of it, you may sense that, okay, this might be a cardiac thing because around the vein. So the spatial location and temporal location should be taken in account both together when we just looking at the signals, especially you have low sampling rate. For example, if you see activity around ventricles, it's less likely to be brain activity, but probably it's kind of um, a thing that you don't want to see if you're interested in the cognitive brain function. But take it as a pinch of salt because we don't know how this pulsatile things happening in the brain might be correlated with the brain function too. And this is a kind of a little bit outdated that we say, okay, we see kind of a network that we always see in the literature. It's got good component, but as I said, it might have vascular back component too. So how to denoise it? So let's use a little bit spectral properties. This is the kind of an early proxy in the fMRI literature. It's called fractional amplitude of low frequency fluctuations. It's kind of a tongue breaker. It's abbreviated like this. So it assumes that anything happens in the low frequency is good, and anything happens in the high frequency, which is kind of arbitrarily chosen like this. And then this ratio is kind of mapped to 2D. It's like low frequency, high frequency power ratio, which helps you to sort out your components. So like, okay, green is good components, red are bad, and they're like mixed. But if you have better measurement techniques like multi-echo API, then you're actually measuring different contrasts, like for example, echo time dependent. I mean, about a week or 2 weeks ago, Dan mentioned about this multi-echo API. So if a component is sensitive to the echo, that's probably a component you're looking for because it has like bold characteristics. Like it's like amplitude in the later echoes getting higher. If it's an artifact component, first it has different spatial signature and it is kind of less sensitive to the different echoes. And the component time course is more pulsatile. So using all those metrics and how it fits the curve, how it's sensitive to the echoes, you can also map this to kind of a 2D space, which is kappa and rho. It looks like it can delineate certain components, not only using just temporal properties, but curve fitting, and also spatial properties. Assuming we have everything perfect measurement, we sample everything physiology the way we like. How do we remove it? I mean, probably filtering is the first idea. Like you basically use FIR filter, you just filter out the physiology because everything happens is low frequency, or you just modulate the task very low frequency, you just filter everything out. But you can also do moving average filter, probably a very bad idea. You have two techniques compared here. Like this is the raw data, the blue, moving average, and retro-ICOR, which is a high-order autoregressive process, which I will mention in upcoming slides. Basically, you sample all those signals, and then you put as a multi-order, high-order regression to remove out. And if you look at this power spectrum, so blue is this signal we measure, and you see the peaks that are cardiac pulsations. And if we sample them and measure them with the peripheral measures and using high order regressive process in the image space, as retro-ICOR mentioned, we successfully trim out the peaks. So the left power is kind of everything but not the peaks. But if you just go and use the first smoothing function, and then everything falls down. Basically, it is very too conservative. Like it just filters out everything, and probably something that is signal interest will go out to. And yeah, the sampling is also thing. The regression part. I mean, regression is mathematically probably needs another session of seminar, but I just want to emphasize few properties of the how two signals could be correlated, uncorrelated, linearly dependent, or independent. Basically, I mean, there are like tons of relations a two signal could be um, interrelated. It could be like transient, it could be linearly dependent, although the correlation it could be uncorrelated but still linearly dependent, or like orthogonal, for example. Or if it's orthogonal, then you guarantee that they're not correlated, but it's just a subset of a huge area. So if you even regress the signal out, they can still be correlated. That's the message I want to give. So regression doesn't guarantee that correlation will be removed. I have an example here. So the blue is the signal that we measure, and the red is the signal we measure from the periphery. It resembles a lot. But if you just go and apply a linear regression, y equals ax plus b, the the leftover signal is not much different from the initial signal, because it only explains the certain variance of the signal. So what people do is they create multiple versions of the signal, kind of shifted variance, and then try to do higher order regression. And the other approach is kind of, okay, let's orthogonalize whatever in the signal I don't want to see, whatever the signal I measure. So here is another example. So it's actually the same time series. So the black is the observed signal and the red is the signal we don't want. And if we orthogonalize, which is a technique called Gram-Schmidt orthogonalization, now you have a completely different signal that is not correlated with your initial signal. But now it comes to the interpretation of it, like if this signal is completely different, and what does it physiologically means? So you basically remove everything out of it. So if you even if you do the brute force, then it becomes the interpretation might be harder. Um, so yeah, um, what is in the literature is using multi-dimensional, not multi-dimensional, but higher order regression. So you basically build a matrix. I mean, here you see the bold time series, which is the signal we measure, and you have tons of signals, might be interesting or not interesting. So the interesting ones are regressor of interest, could be your model that is you're studying, like your cognitive task or your um, uh, or or your task of interest. Could be resting seed time series. And there is an area called nuisance regressors, and these are the signals you don't want. It could be something with the periphery, like the signal in the finger or like respiration. But pay attention, like those signals could be related with the task you're measuring. So that's kind of an important thing to see. And the common trend is like you put a lot of ramp functions here too. That is because of as the scanner drifts I mentioned, and also the statistical properties. The ramp function doesn't help us to run statistics. But assuming your scan is, for example, few minutes rather than 10 minutes, a ramp could be a half cycle of a very slow oscillation. So you may be removing some biological process that is very slow too. Coming to the little bit how we do in the console and analysis to how we handle these signals. AFNI, I mean, Paul Taylor mentioned this a bit in the previous seminar. There are basically two sides. So there's physiology analysis and the fMRI conditioning, let's say, fMRI pre-processing. So physiology is we get the signal and you see either cardiac or respiration in a text or 1D format that the PhysioCalc program understands, and you give how fast you sample it. So it's basically your amplifier, it's biopack. And you need to emphasize how fast you measure the fMRI signal because it needs to be subsampled so that it's aligned in that. And you need to give how many volumes you have in the fMRI images and also slices, because number of slices is important as it will cause delays if it's an EPI thing. Because the first slice is happening, for example, at the bottom, and then last slice at the top. If it is, then there will be a TR delay in between. And in the AFNI side, you can use all type of techniques I mentioned, despiking, aligning, regressing, or like even masking if you want. And the physio processing comes with the user interface. It shows the peaks and troughs, and in this case, just the peaks. And then you need to visually look because a finger motion can cause, I mean, if you focus here, kind of, in this case, it's not extreme, but if it could be a spiky thing, it could be like a blank or completely lost measurement. And it's also nice to show that how fast the peak to peak interval is, like, blue and the red. So this changes in time. So we feed that into uh, the regressors here in the nuisance. And then these are the things that we are not interested, or these are the things we are interested if depends on the study. Then we get beta maps that are related with those pulsations. I will also mention about a little bit the indirect modulation. I mean, I basically till now I talked about direct things like getting faster, try to sample it, filter it out. But there's also indirect thing makes things even more complicated. I mean, for example, the respiratory volume. I mean, not respiration itself, but the amplitude of respiration. So if you look at here, the respiration amplitude, which is kind of an envelope of this, is a slowly happening thing, way slower than the respiration itself, is changing the signal we measure. A step further, a more derivative, heart rate variability, for example. I mean, this is a study from Katie Chang. I put the link over here. It's potentially showing two time series that correlation is changing window to window. And you see how the correlation changes window to window is shown here at the bottom. And at the top, you see in that window how fast heart is beating, basically, heart rate variability, um, how it is variable in that window. And it shows some resemblance. So there's a level of complicated things happening in the body, like heart rate variability changes, could be potentially modulating how signals are in intercorrelated to each other. This makes the direct time course analysis even harder. So it creates more complicated methods to look at dynamic functional connectivity, for instance. This is a study kind of that tries to directly not solve, but disentangle um, the physiology and the task we are measuring, which is a little bit clever way. So we just modulate the physiology. I mean, we don't want things happening in high frequency. Let's say we can ask subjects to inhale CO2, and this could be slow. This could be slow. And we can have in the same time, which is separable tasks like memory task or visual stimulus. And then we can have, so basically you have two tasks. One is like more physiological or say vascular task because CO2 will cause blood flow increase, a vasodilator. And then you have a visual stimulus. And then that will cause actually very interesting results. So you basically have two networks that have two different time series that have a significant overlap. This indicates, for example, this is like a default mode network, and there's an overlap with the vascular task. Looks like default mode network. There's like significant amount of overlap, which says, okay, same spatial area, there's vascular contribution. And if you look at visual stimulus, for example, the vascular task, the CO2 inhalation, this has huge overlap still around here too. Um, so these are disentangled in time, but still entangled in the space. So this brings us to the kind of an understanding, like maybe the only temporal separation is not enough to understand the signals we are measuring. I'm slowly reaching the end of my talk. I have like 4 or 5 slides. I'll talk about a little bit image registration that are tangentially related with the physiology time series thing. This is kind of a analogy I'm making. I mean, most of the fMRI studies, we do rigid body registration, but there is a thing called nonlinear registration, which is deformable. So the things we measured and I mentioned till now is happening in time. So think about the house with a room. The the light of the room is turning on and off. That's what we are measuring. But there are things happening in morphologically too. So like it's kind of interesting, but the size of the window getting bigger. I mean, there might be kind of areas in the brain that gets larger, um, that is accessible through um, um, spatial analysis, which is called nonlinear deformation. So you need to morph one image to the another, uh, which is nonlinear registration. A typical code is for the ANTS registration is commonly used. So for example, you have snapshot of a brain, and then you did again, and it looks slightly different, for example. It's not that brain translate or moved, but it's just certain area of the brain is different shape. Um, in this case, it's a little bit exaggerated, focus on here. So then you do the deformation. It says, hey, the bright areas, you need to expand these areas to match with the image. So you need to expand this area, which is white, to match with this gap here. And then once you warp it, you have the image at the beginning. And then if you do this repetitively, the images we measure with the fMRI, which is kind of a proxy for displacement, it's very noisy thing, the measurement, but it highlights the areas that is kind of pulsatile, and there are areas that are not motion sensitive. So that might be an informative thing to translate the signals we are measuring uh, to more physiology sensitive. So on the top is the images that we measure, looks like this. For example, if you focus on the time series at the top here in the AFNI command line, AFNI user interface, if you do the warp time series, it suddenly becomes this task related, which is in this case breath holding. It becomes very active. So it kind of makes it sensitive to this up and downs. And if you look at how concordant these are, saying that the original measurement we did and the motion sensitive, it looks like the compartments in the brain that are very physiologically relevant. For example, the walls of the inner ventricles, or the veins around the brain, or like fourth ventricle, depending on the task. So this might be kind of a external boost that we can do to help understand the physiology. So I will conclude with some take-home messages. I think I'm on time. I mean, this is not my word. I haven't stole it from Bob, but always look at your data. I mean, the thing we measure, how we measure it, and what does it mean, and probably an iteratively going back and forth to understand. It helps a lot. Always acquire physiology. I know it is very. Sometimes people easily miss that because you need to use multiple computers in the scanner side. It makes things slow, and it's also another pipeline. But at least for respiration and heart rate, it helps. Yeah, physiology might be both noise or signal. Depends what you're looking. And I think this haven't been said enough in this seminar series. Design a task paradigm that helps to disentangle source of signals, and try to look at your physiology, and also design a pipeline that helps you to ask questions and then delineate the task-related activity that you're interested in your research. And with that, I conclude my talk today. If you have any questions, I'm happy to answer. And we probably need a new version of this recent picture. We have new post bags. So sorry about that. This is the most up-to-date one of our lab. I'm happy to answer your questions. Thank you.
The last slide, the last point you made about the pipeline, I just want to that quickly, that's all. But the last point, the last slide, last point. Yeah. That's missed it.
Okay, all right. Any comments or any questions? Looks like
Yeah.
everything is understood. Or was so simple? Yeah. Yeah.
And we know that your different parts of the brain are different. And we're interested, let's say you want to look at it and try to understand, what the brain is doing, right? And so it's important to understand also with regarding physiological signals and regards to things of that nature, but also where activity is reported to be happening and how that shifts with respect to task or training or whatever, is an important variable that to consider. So you want to think about like things like uh, let's say you want to for skill acquisition, for example, or mastery, right? The transit how you would think about these things with respect to fMRI and how you, but you also have to account for natural fluctuations in signal.
Correct.
That could be a potential confound.
Correct.
So I guess how can we, despite the challenges that you've outlined, still utilize fMRI as a useful proxy to understand neural activities with respect to task design and with respect to understanding things about what the brain is doing cognitively.
I mean, very good question. I mean, we do almost everything in the task fMRI based on baseline. And there's an assumption that a baseline condition is task-free, that nothing happening. But there are a lot of studies showing that that baseline is actually getting prepared for the task. And there's a lot of task-related post-shoots, undershoots, pre-shoots, and other stuff too. And there's a lot of physiology happening. But assumption is we scan long, we do repetition of the task, and then we hope the baseline averages out those variables.
Makes sense.
Yeah.
Thank you.
Yes, yeah, you're welcome. Thanks for coming. Thanks for the online audience. Okay, we're done for today.